Good evening, everyone. I welcome you to the webinar on mechanical HVAC and low energy cooling today. I'm Yashima Jain and I'll be moderating today's session for you. Next slide, please. Now, first, I would like to acknowledge the support of the Department of Science and Technology and the Ministry of New and Renewable Energy. I would also like to acknowledge the support of sponsors and affiliates of Solar Decathlon India. Next slide. Now for the results that all of you have been waiting for quiz 1. Now the winner for quiz 1 is Satyajit Potluri, who scored 50 on 50 in this quiz. And the first runner-up is Karthik Rajesh S. Both Satyajit and Karthik are from the SRM Institute of Science and Technology. And the second runner-up, we have a tie among 3 participants. They are Abbas Syed Nuruddin from Aligarh Muslim University, Ayadi Mishra, and Shailesh Singh from SPA Bhopal. Congratulations to all of you, and we will be in touch with you to distribute your prizes. Next slide, please. And here are the top 5 leading teams in the learning of the self-learning modules. You guys are taking the best advantage of the self-learning modules for your Solar Decathlon India entry, and we congratulate you. Next slide. Now for today's announcements. First, we want to apologize that some of you have had issues with the learning platform. You might experience some difficulty as we are trying to fix these issues over the next couple of days, but hopefully that will be the end of it. Next, we have some potential industry partners that are interested in collaborating with the teams, and that's you. So the details of these companies will be on the Learning Online platform and also will be emailed to your team leaders. Next, the faculty leads and faculty advisors, please note that the faculty conference is from December 18th to December 20th, and this will be a virtual conference. And last, there's another quiz coming up to sharpen your learning. And that would be quiz 2, which will be held in the second week of December. And it will cover modules 6 to 10. Next slide, please. Now today's webinar is being conducted by Peter Ramsey. This is Peter's second webinar in our series, and he is joining in from the West Coast of the United States. So good morning to you, Peter.
Morning.
If you missed this the last time, Peter is the founder and CEO of Point Energy Innovations, a new consulting firm focused on working directly with owners and developers in the US and globally on the next generation of profitable, low energy, high performance, and decarbonized buildings and industrial facilities. He has received numerous awards, including the Renewable Energy Innovator of the Year, and ASHRAE's prestigious Award of Engineering Excellence, an award only given 4 other times in ASHRAE's 100-year history. He is a graduate from UC Berkeley and a fellow with ASHRAE and the Association of Energy Engineers. For over a decade, he has taught at the Stanford University. Now, we also have with us today Samit Bhaumik as a panelist. Samit is the director of Vera Tattva Engineering Consultants. He specializes in doing high-performance building design at no added cost. Samit and Peter have worked together closely on Infosys buildings. Welcome, Samit. Now today, Peter will discuss different types of HVAC systems and how to do good design of HVAC systems for your building. As always, feel free to send in your questions at any time during the webinar. We will take as many questions as time allows during the session. With that, it's over to you, Peter.
Thank you very much, Yashma, and good evening to you all. I'm looking forward to this morning, and I just wanted to let you know before I start, I do have extra time after we conclude. So if you want to stick around and ask questions, I'm more than willing to do that for, however long. So I'm very excited to talk today about mechanical HVAC systems, heating, ventilating, and air conditioning, and low energy cooling, LEC for short. So this is something I'm very passionate about. I've spent a better part of my career thinking about mechanical systems in buildings, and have been working in India for the last 10 years on a variety of projects, mostly with emphasis. So this is really very near and dear to my heart. We wanted to start today's session with a question, a poll, if you will. And the question is, what type of cooling system do you have at home? And there's no right answer. We'd like you to type this in. Yashma, if you could explain.
Yes. Yep. So I have sent a link in the chat window, and we would like you to submit your responses there, and then we will share the results. So yeah, the link is in the chat window.
So go click on that link and type in your answer. There's no right answer or wrong answer. We're just curious to see, what you guys, what you have or what you understand you have. So we'll give it a couple minutes for you to connect and type in. And
yep.
Now, while you're typing this in, I will tell you what type of cooling system I have at my house. I live in a city called Oakland, California, right next to San Francisco. And we have a Mediterranean climate, which means it doesn't get too hot, doesn't get too cold. It's a nice climate. So in my house, I do not have air conditioning. There's certain days when the temperature will get up to outside, 30 or 35. And so the house gets hot, but we don't have very many days like that. And if a day happens like that, I'll get a fan. In my office and most offices in the San Francisco area, including Silicon Valley, there is air conditioning, because when you put a lot of people in a building with computers and lights, like we talked about in our load discussion last time, it does add up and you do need air conditioning. So we have a central air conditioning system. So Yashma, do we have some responses coming in?
Yes, the results are ready, and you can refresh, Peter.
Okay. There we go. Great. Okay, so it looks like the number one answer is split AC. This is the word cloud. The size is proportional to the number of answers. But it's just interesting to see evaporative cooler. Desert cooler is also evaporative cooler. Window AC, that's, yep, we have a lot of those in the US. Natural cooling and fan, split AC. So yeah, interesting. Fans, air conditioners and fans. Okay, nothing. So there's a couple people that have, like me. We have to remember that traditionally, air conditioning is a relatively new technology. It's only been around for not more than about 100 years. And so people didn't have air conditioning, even in very hot climates, until more recently. So the first question that we have is why cooling? Why do we have cooling in buildings? The first answer to that is ventilation air. If we bring in air into a building, we oftentimes need to and want to cool that air. And in many parts of India and other parts of the US and around the world, dehumidifying that air is a very important activity. Air conditioning was originally developed by one of the pioneers, was this guy named Willis Carrier. And the first thing that they were trying to accomplish was dehumidification in buildings, not necessarily cooling. Cooling air also dehumidifies air. Another reason why we have cooling is the building envelope. Sun shines on the building, it's hot outside, that heat gets transferred inside of the building. And then the other reason why we have cooling in buildings is internal loads, right? People, lights, computers, all those things create heat in buildings. And if there's a lot of it, it can actually add up, and that will require cooling. So it's always good to think about why we have cooling. If you're interested in this more and didn't have a chance to attend my lecture relating to loads, I'd encourage you to go back and watch that. So what I want to talk about is cooling systems. If we talk about the source of cooling, the way we're going to do this is we're going to talk about the source of cooling, the source of heating, if you need heating, and there's some buildings that do need heating in India. And then we're going to talk about how you distribute the heating and cooling in a building. Okay, so there's conventional systems and there's low energy alternatives or low energy systems. And for your solar decathlon project, you obviously want to be thinking about what are the low energy alternatives. So I'm going to talk about some of the conventional systems. When you get the slides, more of them will be shown and you'll be able to look at them. You can look these things up online if you want more information about them. So on the conventional source of cooling, the first is the vapor compression cycle, right? And that is the heart of most air conditioning systems. And that's where we, and hopefully you've seen this diagram before, but we use a refrigerant to move heat from the building to outdoors. And there's a compressor. I very much urge you to either look it up on Wikipedia or watch some YouTube videos about how the vapor compression cycle works or how refrigeration cycle works. Very interesting, but it's a very important part of all air conditioning systems. So split system, many of you said split system. This is what split systems look like. This could be anywhere in the world. I've lived in many countries. I've lived in Asia, including Thailand and Philippines. I've been to many countries in Asia. Split system is very popular. In Europe, in historic buildings that didn't traditionally have cooling, they're now adding cooling as temperatures get warmer, and you'll see a lot of split systems. And even in the US, split systems are now gaining a lot of popularity. And the key thing about split systems is they have the outdoor unit that you see here in the photograph, and in the right hand side here, this diagram or product photograph. And then you have the indoor fan coil. And some of these fan coils are just mounted on the wall, like the one you see here, but there's lots of different configurations for the indoor fan coil. Now, on the lower left, for all the cooling technologies, I'm going to have a box that says the size and the efficiency. And the size in tons of cooling is just, you know, the relative size. It's a metric we use. In Europe, they use kilowatts of cooling. And, you know, typical size for this is 1 to 5 tons. Most of the ones you see in this photograph are probably in the 1 ton range, maybe 2 tons. And then the efficiency numbers are the kilowatts per ton. So you want less kilowatts for every ton of cooling. This is kilowatts of electricity for 1 ton of cooling. So the lower number is better. So the range of this system, the split system, is very wide. Some are very efficient and some are very inefficient. Another very popular type of cooling or source of cooling is a split system or a package, not a split system, a package unit, rooftop package unit. And this is more for commercial buildings. And you'll see this when you look on top of, you know, low-rise buildings. 1- and 2-story buildings will have this kind of thing. And it comes in much larger sizes, 5 to 100 tons of cooling, and generally about same efficiency with a split system. And then also popular, and I've seen a lot of these in India, is an air-cooled chiller. And the difference between a package unit and a chiller is a package unit makes cold air and you have ducts connected to that package unit. This chiller makes cold water. And then we take the cold water and we can pump it around the building and use that cold water in fan coils or other ways of delivering the cooling. So very popular in larger buildings, and we see a fair number of this. And notice that it can get to fairly large sizes, and its efficiency is still around that 1 to 1.4 kilowatts per ton, similar to the other equipment that I'm showing you. Then we also have water-cooled chillers, and this is where we have a unit that has a compressor and it's connected to a cooling tower where we use water, we evaporate water to reject the heat from the chiller, and the chiller makes cold water. So this is a water-cooled chiller instead of an air-cooled chiller. And notice the fairly dramatic improvement of energy efficiency. The kilowatts per ton went down from 1 kilowatt ton down to about 0.5 kilowatts per ton. So water-cooled chillers use a lot less energy. That's great, right? But the problem is the cooling tower does require water, and there are some areas in India, in the US, and other countries where water is in short supply. And so this has applicability, but not in all cases. It's used typically on large buildings, and the size can get quite large. It's a good thing to use where you have water recycling or water treatment on site. A lot of the tech companies in India have their own water treatment facility. They're treating the wastewater, they're cleaning it, and then it can be used in cooling towers for evaporation water. So I like to think about this spectrum of energy efficiency where the left is more efficient, the lower kilowatts per ton, and the right is, is more efficient on the left and less efficient on the right. And we can take different systems and put them on the spectrum. There's other metrics for energy efficiency. One is called the energy efficiency ratio, EER. And then you also see sometimes COP, which is coefficient of performance. They all are relatable, and there's a formula to convert from one to the next. I like to use kilowatts per ton. Some people prefer to use EER or COP. Okay, let's get one more question. I like to get you guys involved in thinking a little bit. So what are some of the non-compressor based traditional cooling systems that you might find in older buildings? You might find these in older buildings. So I'm talking about a split system has a compressor in it. So go ahead, take this poll. The link is in the chat. Quickly type in an answer. One of the hints that I'll give you is that some of the answers were in the last word cloud that we did. Is it open or ready, Yashima?
Yes, yes. The link is in the chat window, and you can submit your responses.
Yeah.
Yes.
So when we don't have a compressor, we use less energy. Compressors use a lot of energy. So I want you to start thinking about what are some of the systems that use less energy? And those would be the ones that don't have compressors. And it doesn't have to be just for your home. It could be for any building. And there's many answers to this, right? So there's lots of different types of non-compressor based cooling for buildings.
So Peter, we have around 45 responses. Should we wait for a couple of more minutes, or? Let's
go ahead. Go ahead and post them in.
All right. Yep. Okay. Peter, we have the results.
Great. Okay, so here we go. Evaporative cooling. and desert coolers are similar. That's by far the biggest answer here. And if somebody asked me quickly, I would have said evaporative cooling. So, but there's some other very interesting things here. Thick wall sections, that's thermal mass. Wind tunnels or natural ventilation, getting air to move through buildings. Fans, yes. It's probably the most common non-compressor cooling system in India and most countries are fans, right?
Absolutely.
Yeah. And I see some other interesting courtyard water systems and yeah, louvers. Yeah, so that's great. Lots of very good, and trees. Trees are really, really good. Trees create shade and therefore cool temperatures down. And I'm sure many of you have been in a part of town where there's lots of trees and another part of town where all the trees are gone. And there's a real difference in temperature where you have trees creating shade. Some cities in the US will actually pay people, residents, money to plant trees on their street because they know that if those trees grow up, it will cool the neighborhood down and they'll use less air conditioning energy. So great, thank you for participating in that. I did want to share some of the things that I've seen as I have traveled through India. Natural ventilation is probably one of the oldest ways of providing cooling. And you can see there's lots of traditional architecture in different countries that will give us hints on how to do the natural ventilation, right? This is an example from India on the left. And then evaporative cooling, there's lots of traditional architecture that uses different forms of evaporative cooling, and that is having water near the building. There are, and so there's lots of other traditional things. Let me just show you, I have a few more here at the beginning of these slides. One thing that is really important to think about is what's the climate in your area? And there's certain climates in India that have dry times of year where evaporative cooling and passive low energy, dry or cool times of the year, that these passive low energy strategies work very well. So, you know, another very old way of providing cooling to buildings is thermal mass and nighttime purge, right? If we have a temperature difference between daytime and nighttime, usually in the drier climates, we can get a hot day and a cool night. So during the day, we just keep everything closed. At night, we open all the windows, let natural ventilation come into the building, cool down the building and the thermal mass of the building, and then we can close the windows during the day again. So thermal mass is very useful, especially where you have a nighttime temperature swing. Evaporative cooling is very big. A lot of you pointed that out, and there's lots of different types of evaporative cooling systems, but the main concept is when we evaporate water, it does, in essence, absorb heat and deliver cool air. The one thing about evaporative cooling is it doesn't work when it's humid, and it does add humidity to the building if we're doing direct evaporative cooling. There is indirect evaporative cooling. If you're interested, you can look that up, where it does provide the cooling benefit, not as much, but it doesn't add the humidity into the space. And then there's even on the right here, I'm showing a combination of indirect evaporative cooling together with the direct evaporative cooling, which is where you get the maximum amount of cooling from evaporative cooling. So very low energy. Look at our kilowatts per ton. Remember that our split system is at 1 to 1.5 kilowatts per ton. These systems can be down at 0.1 kilowatts per ton easily, or maybe a little bit more depending on the fan system that you use. The fan energy is where the kilowatts come from for evaporative cooling. Again, you have to have water available, and it has to be clean water when you're doing, especially if you're doing it directly into the building. Another thing on low energy cooling, moving to more compressor-based systems and such, is for every category of equipment like split system, there's a more efficient alternative. So I'm not saying split systems are bad and we need to stop using them. No, we need split systems, but there's very efficient split system and there's very inefficient split system. And so when I'm working on buildings design, and if my client says we have to have a split system or we have to have air conditioning, I will do two things. I will work to lower the requirement by having a better building envelope, lower loads, and then I will find the most efficient version of that system, split system or whatever it might be. This is a graph looking at package units from this company called Lennox. And energy efficiency ratio, higher is better. And so you can see the difference between these minimums, but the federal minimums in the US and many of the pieces of equipment that are sold just barely meet the federal minimum. And the difference between that and the most efficient package unit that Lennox is selling is almost twice as, well, no, I'm sorry, the graph doesn't start at 0, but it's significantly better than just the minimum. And so I see that so often that the most efficient within a category is using at least 1/3 less and sometimes half as much energy. So that's something to think about. Here's another example of that, chillers for bigger buildings. The chiller without the variable speed drive, and this is a graph of, excuse me, kilowatts per ton. And so lower is better. And with the variable speed drive, we get much lower energy consumption, right? And these are at percent loads, you know, what is it, 50% of the maximum capacity or whatever, right? So all the different types of equipment have more efficient alternatives. Another system that we're seeing more and more is a variable refrigerant flow system. And that's a system where we can put together all the different zones into one centralized system. It's very much like a split system, but it's where you're combining the fan coils into a heat recovery unit and to an outdoor unit. These are optimized versions of split systems. They work very well. They have variable speed compressors, variable speed fans, the whole bit. They're very much optimized. And if you do have a climate where part of the year you need heating, the interesting thing about variable refrigerant flow systems is that they can provide heating in one zone and cooling in another. And they can do heat recovery at these, the heat recovery controller. And so you have a much lower load on your compressor. And this does happen in commercial buildings, that you have part of the building in heating and part in cooling. So looking at the more efficient cooling, I don't have time to cover them all, but again, in the slides that you'll get later, there are other alternatives. You can look at this most efficient to less efficient and look at it in terms of one of the metrics, kilowatts per ton, or whatever metric you want to use. And then you can compare and select based on that. Right. So, and you want to choose one that if your load for your building is 100 tons, you want to have one that's very efficient at 100 tons. You don't want to choose something that's very efficient at 1,000 tons and then you bring it down to 100 and it's less efficient. So generally you want your load and your equipment sizing to match and find something, within that category of the size for your building that's the most efficient. Okay. So there's a thing about heating. Not a lot of buildings in India need actual heating, although some climates, northern India and such. But we also do need heating for hot water heating. Some of you are doing multifamily projects. And then cooking is another area where we're using heating. So there's this whole concept now of trying to decarbonize heating. And I want to get into that a little bit. Let's see. Oop, hold on. Oh, okay. Here's a poll here. I'd like you guys. Yeah, go ahead, Yashima.
Yeah. So as Peter mentioned, we would like you to take a poll here. And the question is, what is the primary source of water heating at your home or the home where you grew up? So the options are solar water heater, electric geyser, gas, heat pump, no hot water, or you're not sure about what the source was.
Yeah. So if you
Yep.
could just do that quickly, that'd be great.
Right. So I think we'll end the poll now in 3, 2, and 1. And I'm going to share the results. So
There we go. Okay.
65% have electric geyser, 17 gas, 16% at solar water heater, and 1% each at heat pump or no hot water.
Great. Great. Very interesting. Yeah. So it's not a surprise that electric geyser is the predominant answer, and that solar is big. It's actually a little surprise to me that there's a fair number of people who have gas water heating. In the US, we have mostly gas water heating, but we also have solar water and electric, and a little bit of heat pump. Okay, so
Yep.
that's great. I want to talk about heating, and it applies to water heating, but also space heating. There's lots of different ways of doing it, but one of the ways is natural gas, using natural gas or methane gas, propane gas, connected to a boiler where there's combustion and we get heat out. And a therm that I'm using here is a measure of quantity of gas, and it's equivalent to 100,000 BTUs. But just a measure of quantity of gas. So usually most of these boilers that burn gas are about 80% efficient. When we use electricity in electric resistance geyser or electric resistance space heater, like you see this photograph here, there's lots of different types of electric resistance heating. It's exactly 1 for 1. If you put in 1 kilowatt of electricity, 1 kilowatt of heat comes out. And so you'd say, well, that's a lot more efficient. But in some areas, gas is cheaper than electricity. Electricity is a very high form of energy. It's very, valuable, flexible, and a lot goes into creating electricity. So a lot of places are still using the gas where it's available because it's oftentimes cheaper. The interesting thing is the heat pump. And the heat pump uses, again, our refrigeration cycle, vapor compression cycle, etc., to move heat from outside or from one place to another. So we can move heat from outside into the building to provide heating, even on a cold day, or we can move heat from the air, low density heat, into hot water. The compression cycle allows us to change the temperature up to a higher temperature. So 1 kilowatt going into a heat pump can yield 3, 4, or 5 kilowatts of heating. So heat pumps are the very efficient version of electric heating. They're more expensive, they have more moving parts, so they do have their place, but they're significantly more efficient, and we're seeing a huge growth in the use of heat pumps. So again, just looking at it, if we have an electric boiler for hot water heating, there are some losses on the tank. So we need about 102 units of electricity in to give 100 units of water heating out. With a heat pump, notice it's 33 units in and 100 units out. So significantly better, the heat pump. So we're going to see in the coming years, heat pumps become the preferred way of doing water heating, and if needed, space heating. So there's lots of heat pump water heaters are starting to come out. The one on the left is integrated into the tank. Above on the top of the tank is a heat pump. But there's also ones where it's like a split system. The outdoor unit is connected to a compressor, and then it creates hot water that can then go into a tank. This one on the right uses CO2 as a refrigerant, which is very good environmental refrigerant, has low impact on the environment. There's also very large commercial heat pumps that make hot water. This is what we call air source heat pump. It's like an air-cooled chiller, but it's an air source heat pump. and it can make hot water that we could use in a large apartment building for domestic hot water, or where there's restaurants or whatever it might be. Very efficient. I did also want to quickly talk about gas cooking. And you guys have the LP gas and different types of gas for cooking. Gas, when you burn it, it does release nitrous oxide, carbon monoxide, formaldehyde, lots of things that are not so healthy. But we do it anyways. I have gas cooking in my house because it's affordable and cheap, and everybody is doing that. But as it turns out, it's not so healthy. And it's also not very energy efficient. 30% of the heat energy goes from the gas into the pot, only 30%. When we move over to electric cooking, it gets much higher. And the most efficient version of electric cooking is called induction cooking. And there's everything from small single burner induction cookers you can plug into the wall in your kitchen, all the way up to commercial equipment that does induction cooking. And this gets about 80% of the heat or the energy right into the pot. And it uses a magnetic field to do that. So it's better air quality. There's not as much heat escaping, so it's safer. You're not heating up the surface. The surface doesn't get hot. It's easier to clean, and it's very precise and rapid form of heating pots and cooking. So we're going to see lots of induction cooking, and this is the most energy efficient way to provide cooking. So I would urge you to look at induction cooking in your project. And if we could connect this induction cooking or heat pump, electric heat pumps to renewable based electricity, solar energy, then we have a zero carbon heating and cooking. Very important, very good thing, because whenever we're burning gas, we're emitting CO2. And so it's a problem over the long term. We really want to connect a renewable based electricity to all electric buildings, and that's our fully decarbonized building. Yeah, and you guys are doing the solar decathlon. The idea is that you have that renewable based electricity right at the building. And so you do need to and want to have an all electric building. Okay, so distributing heat and distributing cooling in buildings, we use pumps and fans. The interesting thing is pumps and fans account for, depending on the building and a variety of things, 25 to 50% of the HVAC energy. Your split system, there's a fan outside and there's a fan inside. And if we measured that system, we find split systems are pretty good on the fan energy, but it's probably around 50% or 25% of the energy of a split system is used in the fans, the outdoor fan and the indoor fan. So conventional distribution systems, we have fan coils. Sometimes they're exposed, sometimes they're concealed, sometimes they're, on the wall. Lots of different options for fan coils. And the idea there is that we can bring refrigerant or cold water to the fan coil, and then the fan blows over a coil and transfers the cooling into the air, and then we blow it around our space. In bigger office buildings, we use a variable air volume system with what's called VAV boxes. So that's where we have we vary the amount of air that goes into the space based on the temperature. So it's cold air and you want less of it or more of it. And so variable air volume with VAV boxes. The low energy distribution systems, and this is mostly as it applies to commercial buildings. There's lots of options here, but I just wanted to show you a couple of them. One is this idea of a raised floor, and you have very low energy, low fan energy because there's no ducts. You're just putting the air into a floor, plenum, and then you have floor diffusers where the air can come up through the diffusers. We also get, we've used very successfully the radiant cooling, where we put tubes into a slab and then we pour the concrete slab and then we're just cooling the slab. And so when I first started working with Infosys years ago, we did a building like this and it was very successful. And I'll talk a little bit more about that later. In Europe, they use radiant panels in the ceilings for office buildings. It's a fairly popular low energy way to distribute heating and cooling. You can do both. You put hot water or cold water through ceiling panels or through the slab, right? The reason why radiant is so efficient is that, and so good, is that these 2 bags of air are equivalent to 1 small cup of water. It's a very small, it's not a full cup measure, but it just like a few milliliters of water. So it's about a 3,500 to 1 ratio of the volumetric heat capacity of air compared to water. So water is very dense, and pumping is much more energy efficient than blowing air around. So that's why radiant makes sense. And so we can put radiant in the slab. We still are going to need to bring in fresh air. And so we do have the requirement for fresh air systems when we do radiant. Another system that is out there that's low energy is called chilled beams. And again, this is applicable to more commercial buildings, but very low energy. And you can look that up if you want a little bit more information on it. But we couple these systems to a dedicated outside air system, an air handler that brings in fresh air. So we might have, let's say, a fan coil, radiant system, or chilled beams, and then we still need an air handler that brings in air. Now, that air for ventilation is much less than what we need for air conditioning. So these air handlers, we're talking about a commercial building, it's a very small air handler, about 1/3 of what you would have if you had a full air-based air conditioning system. So if we have a dedicated outside air system, we can filter the air, we can dehumidify the air, and we can create great air quality in the building. And that's really important, is that we want low energy buildings to also be very healthy buildings. And as you know, many cities around the world have poor air quality. And so filtration is a great and simple way to be able to create much better air quality for people when they're in the building, so they're healthier. So it's a really big benefit. And then when we control the humidity, mostly about dehumidification, we can make sure that there's no mold growing in the building, or that it's always a very healthy environment. So yeah, I think I personally think dedicated outside air systems are an excellent way to go, as compared to mixing air conditioning and ventilation. When you mix them together, you compromise both. And so I like to decouple them and separate them. So this you can look at later, but it's a table of some data comparing the different systems and their pressure drop and things like that. This is data that you could use in calculating the energy consumption of your distribution system. I did want to end this section by talking about simple Victorian engineering, and that is to use, we can use good design principles to come up with much lower pumping or fan energy systems. The system on the left is equivalent to the system on the right, and we did the same thing with much less piping, and we were able to get away with 2 pumps instead of 3. So it's cheaper to build and much less pumping energy. And I've done many systems like this where we were able to cut the pumping energy in half through just better design. Okay, so I just want to jump into a few case studies so you can see some of these ideas in action. This is an apartment building in New Orleans, US, and New Orleans is a hot and humid climate. It's similar to lots of climates that we might see in southern India. Never gets cold. It's just always warm, and either warm or very warm. Always humid. It's on the Gulf of Mexico. And this building was done as a very low cost building, so that it could be very affordable for people, lower income folks, but also it was done in a way to be net zero. They did smaller windows. In this area, they also get hurricanes. The smaller windows are good, preferable. They're more durable in a hurricane situation. But you can see on the roof, they did split systems. So they did 1 split system for each apartment. And one of the reasons for that is apartment buildings in the US, most areas, they require that there's 1 meter for 1 apartment, so that everybody is paying for their own electricity. In that way, if you have 1 split system for 1 apartment, the resident of that apartment is paying for their air conditioning. So they did a bunch of split systems. It's maybe not the most efficient, but it's they chose a more efficient version of a split system, and it was very simple, very reliable. And then you can also see on the roof, there's lots of, this is a, from above, there's photovoltaics on the roof to make the electricity for the building. And for the water heating, they had one heat pump water heater for each unit. And it's this type that has the heat pump on top and then the tank below. And because it's always a hot climate, the waste product of a heat pump water heater, the waste product is cold air. Right here, cold air. This climate is always in cooling. So what they did is they just ducted that cold air into the apartment. So it's always a benefit that you're getting hot water and cold air at the same time. If you're in a cold climate in the wintertime, like in Minnesota or Chicago or northern India, in wintertime, if you have a heat pump water heater inside your apartment and it's blowing cold air into your apartment, that's a problem, right? We don't really want that. But if you're in a hot climate, this is a benefit. And so they just put the hot water heater, heat pump hot water heater in a closet in each one of the units. Smart, it's creative, simple idea. So this is the Radiant building I was talking about that we did with Infosys almost 10 years ago now. And the idea was Infosys wanted to test the Radiant. They were a little bit, hesitant in it because it was new for them. On the left side of the building, we did the VAV system, the variable air volume, air-based system. And the right side, we did the Radiant system, and it was a very, large new office building in Hyderabad. And what it turns out is that the Radiant system was 9% cheaper to build than having all the ductwork. I found that in air handlers. I found that very interesting. And the Radiant tubing that I showed you earlier, the energy consumption on the Radiant side of the building was 40% less than the air side of the building. So it's the same load, same number of people, same function, all these things, and they got a significantly lower energy consumption. So this began a process by which Infosys started designing a lot of Radiant buildings, and so now they have dozens of these buildings, and they're very, very low energy. I also wanted to share with you a project I did in California called the Packard Foundation, and this is a small office building. And this building was a very significant building in the US because it showed that the net zero building can also be a very beautiful building. This was designed as a net zero energy building. And before this building, a lot of people thought, well, a net zero building, it's going to be ugly and sort of weird and have this, weird solar panels on it. But we did it in a way that was just, beautiful. And you can see the results. This building, we started by thinking about lowering the loads, right? What I talked about last time. We had external shades that are operable. When the sun's on them, they come down. When the sun's off, they go up. To let in more daylight, so the electric lights dim down. So we did a lot. We had good windows and insulation in the walls and all that. And then we used the chilled beam system, and you can see the chilled beams in the ceiling of the, this is the conferencing area on the first floor, but done in a really nice way. And then this is a diagram of the building systems. And when you get the slides, you can look at this a little bit more closely. And there's lots of information on the internet about this building. But we did make chilled water at nighttime with the cooling towers. And we did not, and most of the year, we do not need to run the compressor. We just did evaporative cooling connected to a tank. And then we also have heat pumps, air source heat pumps to make the hot water for the building. And then on the roof, there's lots of solar photovoltaics, and we have rainwater catchment tanks. So when it rains, we can catch the water and reuse it for toilet flushing or irrigation, and lots of really nice features, all done in a way that's very beautiful. So it's a great case study. If you're interested in the net zero office building, that's an interesting one to look at. Okay, so I want to end with two things. The first is the secret to low energy cooling. And remember, the main thing you want to be thinking about for your solar decathlon is what is the low energy cooling solution. These should be applied in order. And the number one thing that you can do for low energy cooling is lower the loads. If I have better insulation, shading on my glazing or less glazing, you still want glazing for daylight, so the electric lights are lower, but you don't necessarily want an all glass building, right? But if you can lower the loads, you need less cooling to start with. And so a lot of buildings I work on, we're able to cut the cooling requirement for what would be a standard cooling requirement in half. So where we might need, 500 tons of cooling for a big office building, we only need 250 now. So that makes everything much easier. The next thing is use passive forms of cooling and ventilation. So we talked about things like natural ventilation, nighttime flushing of a building, and then ultimately, it's not completely passive, but it's close to it. Evaporative cooling is a very low energy form of cooling, and there's other ones. Some of them you guys pointed out in that word cloud. Then the next thing is right size. So much equipment in buildings is oversized and it wastes money and energy. And so we always make sure that we're providing enough cooling, but not more than what's needed. And then the next thing is we use simple Victorian engineering for low pressure drop design, the smooth pipes that I showed you, smooth duct work. And then we select very efficient equipment, trying to find, if we're using split system, a much more efficient split system, right? And then the last but not least, we best practice in controls. A lot of engineers just run immediately to controls because they're really interesting and complex. But we use controls that's the last thing, and I don't like complex controls. I like simple controls, but done well. So this is the key to having a low energy cooling system on your design. So I want to leave you with one thing. Last time I left you with a little, interesting information about designers' impact on climate change. Another interesting fact is that 50% of the buildings that are needed for India by 2050 have not yet been built. So you have an amazing opportunity to build buildings that are efficient from the get-go, day one. And we have a problem in the US that we don't need very many new buildings. We really don't. There's still new buildings being built, but generally speaking, we probably only need 10% more buildings by 2050. So we have a big problem. We need to go back and retrofit all of our buildings, which is much more expensive to retrofit a building, make it a low energy building, than it is to just design it right from the beginning. So, you have a very excellent opportunity to, in a sense, leapfrog where the US is and Europe is, where we're stuck with a lot of older, low performing buildings, where India can start designing high performing buildings and make them much more affordable than having to retrofit them. So it's a great opportunity, and I love that you guys are participating in this, and you're going to play an important role in making this next generation of buildings for India efficient. So with that, I will end, and I am excited to take your questions and discussion.
Thank you, Peter.
Yeah.
We have had questions coming in, so we'll take them as we go. So the first question is, what are the conditions to consider HVAC in an educational building?
Yeah, like how do you decide which type of HVAC, right? I assume that's the question. So I get that question a lot for all building types, right? What's the right system for this building? And I could say the cheeky answer is, well, you should go to engineering school and it takes, 4 years to learn. No, but a better way to learn quickly what's the right way to do education buildings is, I've seen literally so many different systems for education buildings or any building around the world. And the thing that's interesting is that I found that the good starting point is, what are most education buildings in your area doing? Let's start with that. So if you're looking at, part of India, I would start by looking, what are other education buildings doing? And do some research on, okay, it looks like most of them are using this type of system. What are some other alternatives that some people have tried? So I would start to see what's out there, and that would give you a good understanding of the direction. And sometimes what I do is I just make a very low energy building envelope, and then I take what people are doing in that area and I just find the efficient version. So if a lot of schools have split systems, one split system for each classroom, then I'm just going to make a very good envelope. It's got good daylight, but not too much solar glare, good insulation, and then I'll find the most energy efficient version of split system available, and I'll make sure that I choose the right size. And that sometimes is good to go. But then you can also look, is some of these distribution systems and cooling sources, you can think about them, talk about them with your team. What about doing radiant in a classroom? That is actually something that can be done, and it's very low energy. What about, can I do evaporative cooling for part of the year? For this, so part of the year I'm using evaporative cooling. Maybe a part of the year it gets very hot and humid, and you have to turn off the evaporative cooling and turn on a compressor. So I would, one thing you could do is go through the slides that you'll have access to and look at the low energy cooling options and say, well, what if I apply this one? What will happen, right? So that's like, to go beyond with what's being done in your area. You can start looking at some of the things that I've shown, and you can do a little bit of research. But I think start with the fundamentals, get the loads down, look at efficient equipment that's currently being used in an area, and then you can look at some alternatives. But you might calculate it out and find that it's good enough. That if you have to make net zero, you have solar on the building, that's your energy budget, the solar on the building. And then if you put these things in the more standard or conventional system, but done efficiently, it might actually fit into your energy budget. And then it's good. It will be recognizable by people in the area who are going to have to build this.
Thank you, Peter.
Yeah.
Next question. In India, HVAC systems are costing us a lot in terms of energy. As an example, with high humidity and high temperature in North India, we prefer ACs where desert coolers and fans are not effective. Any building innovations you may recommend for this region?
So when we say North India, is that Delhi or is that north of Delhi? I'm just curious. Generally, when people say.
Yeah, it says North India, so we have projects further north of Delhi. So
yeah.
So he says Punjab.
Right. Okay. And was the statement that the evaporative cooling is not effective in that statement that was read there, that you read to me?
Yes, high humidity and high temperature.
Yeah.
And where desert coolers and fans are not effective.
They're not effective. Yeah. So, when it gets to a certain point that we do need the compressor cooling, but they're expensive. They use lots of energy, right? That's exactly the issue. And they also emit there's lots of carbon emissions associated with it as well. So, the first thing that we need to do is we need to design the most efficient building possible. And I want to tell you, everybody, right now, that it's possible to reduce the need for cooling by 50% if you design a good building from the get-go. And that is always the best answer, is design a better building. When I say 50% compared to like a very thoughtlessly done glassy building, if we're talking about an office building or apartment building with just so much glass, it's so popular right now everywhere in the world. We can sit down and design a building that's very beautiful to be in, very beautiful to look at, and it uses half of the energy of so that's the first starting point. And then if we select a good compressor-based system, we can get another maybe 25% reduction off of the cooling energy, not the whole energy, but the cooling energy. And it starts to look a lot more reasonable, in hot areas. And, I work in a lot of hot areas in India, other parts of Asia, in the US. We do have to accept the fact that it's hot, and oftentimes it's getting hotter. These temperatures can be difficult for older people, things like that. We need a compressor-based cooling system so that, these places and these buildings and cities can be habitable. We just need to do it in as low energy way as possible. So I think we put all the best strategies together that I'm talking about. We can get the energy consumption down at least by 2/3. We still are going to be consuming energy, and that's where we want to be doing renewable energy. And hopefully, and we're finding in India and other countries right now, the renewable solar-based electricity is the cheapest version of new electricity. It's cheaper than the coal plants now. There is a way forward to make this work. But when we do put compressor-based cooling in a building, it does add cost. There's no way to get around that. And I do work on affordable low-income apartment buildings and things like that, and they can't afford the cooling. So what we do is we get very focused on lowering the loads, and then we use things like ceiling fans, also popular in India. And ceiling fans can really take the edge off and make you feel comfortable without cooling, but it's, there's a certain point where it gets hot enough. It's just not enough, the ceiling fan. But ceiling fans also help quite a bit.
Right. Thank you, Peter. Next question. What is the difference between EER and SEER?
Yeah, so the S, and you can look that up, but S is seasonal energy efficiency ratio. EER is energy efficiency ratio. And energy efficiency ratio is the output divided by the input, and there's a BTUs divided by kilowatt hours. So mixing the units. I don't love that metric, but the seasonal one is where it takes into account that in different seasons, you'll have different energy efficiency. So when it's hotter outside, and you're trying to do cooling, you're going to use more energy. So especially in climates where there's, a hot season, cold season, or winter and summer and things like that, the equipment will operate more efficiently, if it's cooling equipment, more efficiently when it's colder outside, and less efficiency when it's efficiently. So they do an annual average to come up with a seasonal energy efficiency ratio. But look it up online. There's a good definition of that. But it's a good question. It's interesting. Yeah.
Thank you. Next question. How efficient is the VRV system in tropical regions?
Yeah. So generally speaking, it doesn't do this combined heating and cooling I was talking about. It's all cooling. But a good VRV or VRF system is more efficient than a split system because they're generally more optimized, and there's more sharing of the refrigerant, getting the refrigerant to where it wants to go. So the first optimization thing is they have variable speed drives in the fans, a variable speed compressors, the better ones, a variable speed compressors, and better controls. It's just like a more optimized system. So its kilowatts per ton or COP or ER are going to be better than if we just gave everybody a split system. So the VRV, VRF, variable refrigerant volume, VRV, variable refrigerant flow, VRF, same category, but different manufacturers have different, nomenclature. These systems just have better performance. They're applicable in buildings where you have multiple units. So apartment building, office building, schools, the VRV, VRF would be a more efficient version of the split system. If you have water available, you want to maybe think about doing the water-based, cooling tower-based chiller. Sometimes they have water-cooled VRV, VRF systems, and all of those will have lower kilowatts per ton, lower energy. Sumit.
Yeah, so on the VRV, there's nice information available in the cooling in the learning model as well. And one of the big advantages of the VRV system is how you can sort of use the benefit of diversity to sort of reduce the size of the outdoor unit and therefore the capex. So that's so. While energy is one of the decision makers, while choosing a system, but we should also realize that at the end of it, it's also capital cost, which is going to be important. So it's something which has to be balanced with energy, in perspective.
Correct. And
Yep.
yeah, very good point. Yeah. And so in the learning module, that VRV, VRF is covered, and I would urge you to look at that. And again, there's so much good information on YouTube or Wikipedia or these different places that explain how these systems work. So if you're, thinking about it, just go dig a little bit and you'll get some good information quickly.
Right. Thank you, Peter and Samit. Next question. Are heat pumps being used in buildings in India?
Yeah, well, it's interesting because there was one person who said on the water heating that they had a heat pump water heater. So I don't know. But when we started at Emphasis, and Summit can probably add, but looking at heat pump water heating for the buildings and for they have, hotels or residential connected to Emphasis. And so they started using heat pumps. So they are available, although it's more expensive and less common. Summit, do you want to add?
Yeah, so I can see that a lot of commercial spaces, people are using heat pumps. It's very easily available, and it also probably at a certain scale, the cost also works out much better. But at a residential level, it's still not able to replace a geyser. No, we still don't have small size heat pumps which you can sort of retrofit into a bathroom. So that's so that's the reality today. But I mean, there's no doubt there it's growing. It's more easily available, and the cost of it is also reducing by every season actually.
Yeah. So for commercial buildings or apartment buildings, it is available. And a thing, the geyser, it's so cheap. The electric resistance, it's very simple and cheap. And so on the residential side, you'll see the heat pump coming to residential will be second after the commercial ones. Yeah.
Thank you, Peter and Samit. Next question. Can insulation play a role in making air conditioning more efficient in India or the Middle East, or a trade-off with user comfort is observed?
What was the last part of the question? Sorry.
Yeah, in India or Middle East, or a trade-off with user comfort is observed?
Well, I mean, I don't think there's any trade-off with insulation. Insulation is a good thing in lowering the need for cooling in buildings. So it's going to make your building more comfortable. So if we're talking about insulation in the exterior wall, it's very good at slowing down the heat coming from outside and going into the building. There are some climates where too much insulation is not a good thing. And that's where we have climates where it's, hot during the day and cold at night. And we want, and in a large part of the year, it's like that. And we want the building to release the heat at night and not have to open the windows. And so we don't insulate, we use concrete walls and things like that, but it's fairly specific. And there are a couple climates in the Middle East that are not as hot as places like Saudi, mountainous Middle Eastern climates and such. But generally speaking, most of the climates in India are going to benefit greatly from additional insulation in the building, and it will improve comfort in the building, and there's no sort of trade-off there.
Thank you, Peter. Next question. Is there an innovative equivalent to heat pumps using the mechanism of heat pumps, but through non-mechanical techniques like earth, water, etc.?
Yeah, not really. I mean, there are sort of other ways to provide cooling, like ground coupled cooling. And I have a couple slides that you'll see when you get the deck. But there's, like a manual version of a compressor system, like, where you could hand crank the compressor. Maybe I haven't seen that, but it's Generally, when we have compressors and we're trying to provide like high quantity of dense cooling, it does require electricity. But, you know, I do think there's other passive ways to provide cooling. It's just not the same as a compressor-based system. Yeah, I'd love to have a discussion about that, you know, with whoever asked that question, because I mean, there are some interesting, innovative ideas, but none of them are sort of like the same as a compressor. There's just sort of alternative routes. And I don't see an emerging technology right now that is as good as compressor based, but there are some things that are not as efficient, but do use electricity and can produce good amount of cooling. And there's this one electric version of cooling that uses I forget what it's called, but you can get a electric cooler for, you know, drinks and such. You can plug into your car and it does not have a compressor and it provides cooling. It's just very inefficient, but it can provide good amount of cooling. And so, yeah.
Yeah. Samit, you was about to say something.
Yeah, I mean, if I've understood the question right, I think someone, I mean, the question was about whether we could use ground heat or something like that, is what I'm understanding from that. We need to understand, I think, you know, how much is the heat available in the earth, you know, and we should probably also get some analysis or some data about the ground temperature. Sometimes you could get very, you know, really carried away by Google research, and you know, it's important to really be grounded and be aware of what is the temperatures available. So an average ground temperature in a country like India will probably be around 15 or so, or a little more than that, and that might not really give you any heating at all. You know, so we need to be aware of this. There could be other areas or other you know, sources of heat, but you know, ground itself may not be without doing any compression or without any addition of heat, so you might not be able to get any heat at all.
Correct. Yeah. Yeah.
Right. Thank you. Next question. Induction cooking, as you mentioned, is the best way, although does it slow down the process? I'm assuming this person is talking about the process of cooking.
Yeah. So no, you know, I have an induction stove in my house now, and it cooks very fast. It's very, we don't have to wait for, you know, the pot to heat up. It's because it's so efficient and the heat's going right into the pot. The pot immediately gets hot. If I'm boiling water, it boils very quickly. When I'm, you know, frying something or cooking something, if I put it on high, it's very fast, sometimes too fast. So, you know, I put it on to medium or something, like it goes immediately to medium. So it's very quick to respond and very, you know, high quality cooking. The only thing is, if you have to have the right power. There are some of the ones you can buy, you plug in, and it's only, let's say 500 watts. Well, it's not enough to provide, you know, the fast cooking. For a one burner, you want at least 1,000 watts. And then you can do all sorts of cooking very quickly and conveniently and safely, efficiently.
So I have an interesting observation here, Peter. You know, it's on some of the projects I've worked on, and where the client looked at induction heating. You know, in typical kitchens, you have a combination of gas and a little bit of induction cooking possibly. But so when the client started looking at induction sort of heating for the entire range, they cut down on the gas, obviously, but suddenly the electricity requirements went up, you know, and they had to sort of put in additional equipment to manage that. It's something which everyone should be aware of. It's an efficient way, but you're shifting from gas to electricity, so therefore you need to necessarily take, you know, make sure you have electrical, you know, switch gear and you know, generators or whatever it is suitable for that kind of an electrical load.
Yeah. And you know, it's most applicable where you're able to connect that electricity, renewable-based electricity. Yeah. If we're connecting to coal-based electricity, and then it's not really a win to go to induction cooking, right? Yeah. So, but I'm talking about in relation to the solar decathlon, where you really want to be solar powered, therefore electric, and
Right. Exactly. Thank you. Next question. doesn't a slab full of radiant cooling pipes cost way too much, or is it comparable to other air conditioning in terms of cost?
So, you know, the building I was showing, which was an office building, it cost 9% less to build as compared to using an air ducted system. Okay, it's a large office building. You have to use ducting, air handlers, fans, all these things. It takes a lot of labor to install it, and it needs to look beautiful, all these things. So, you know, the radiant actually is quite affordable. You have to, you know, already build the slab, the concrete structure, the rebar and everything. And when you're building the rebar, you just put the piping in there, you attach it to the rebar with little ties, and you just run it through there. And it's actually a very simple way to just embed the cooling into the building structure, which you have to build a building structure anyways, right? So it's affordable way to go. It's not the right solution for every building, but it does have a very good application in you know, lots of office buildings and other types. Infosys also has spent a lot of time doing the radiant ceiling panel. I showed you some ones from Europe, and so Infosys actually developed their own radiant cooling panel. So many of the buildings that they do with radiant, which are very low energy, they don't put the tubes in the slab, they'll put radiant panels hanging in the ceiling. And so, yeah, it's not the only way, it's not just one way to do radiant. There's many ways to do radiant.
Yeah, I mean,
go ahead, Samit.
You can add, you know, I think it's also important to know the scale of the application, how large the building is. I think there's going to be a minimum cost for radiant, you know, in a building. So I think the size of the project also makes a difference. And like Peter said, the type of the application makes a difference. I think the weather in which you're doing it, the region in which you're doing it also can make a big difference to how the economics works out for a radiant system. But in general, you know, radiant pipe in slab in general is definitely less, you know, for a comparable building is definitely less expensive than a conventional system.
Right. Thank you. Next question. For a residential building, which method of cooling can be cheaper as well as long-term maintenance free as well as energy efficient?
Yeah. Well, you know, it depends on the climate, but, you know, most climates, I think the lowest cost way to do an apartment building is make it the building envelope very energy efficient, and then an efficient split system. You know, the VRF will probably be comparable plus or minus, but because VRF is, you know, very refined, it's typically a little bit more expensive, but it will probably be more efficient, the VRF system. But if you were looking for just the cheapest, I would say, you know, good building envelope and very efficient split system. That would probably be the cheapest. But maybe you can get some more energy efficiency out of switching over to VRF or VRV. I don't know, Samit, I mean, do you agree with that or?
Yeah. So you know, I'm sure a lot of people in India will, you know, have not had air conditioning in their houses for, you know, at least in the last 20-25 years. So I think one of the, you know, the lowest energy consuming option is, in my opinion, cross ventilation. Just make sure you have enough windows available, large windows available, and make sure you're ventilated. So even if you're forced to use a split unit or a VRV for some time during the year, you have 80-90% of the time when you don't really need it at all. So I think nothing can beat switching off a unit. You know, that's
yeah. And then maybe ceiling fan, you know. Yeah, and that's an important thing to remember when you're doing your energy modeling and design is you want to have different modes or ways of providing ventilation or cooling at different times of the year.
Yeah.
Right. So when it's cooler, then yeah, we just turn off the compressor, and you can schedule that into your, you know, your energy model when you're figuring it out.
So it's far more easier to convert a naturally ventilated building and do an air conditioning for some part of the year than it is to do the other way around. So if you have a building which doesn't have enough windows and the cross ventilation is not good enough, you're always going to be spending a lot more energy on the mechanical cooling.
Correct. Very good point.
Right. And we also have a following question to high-rise residential buildings, which is if you could talk about other systems than split air conditioning, or energy efficient alternative options for high-rise residential buildings.
Yeah. So if you look at a split system, it's got the fan coil inside, and then outside is the outdoor unit, the condenser with the fan and all that. So in a high rise, we don't really want to do split system because it just is very ugly, and you can't put the split systems, 20 floors away. One of the very efficient ways to provide cooling, it's also, fairly simple, is you have a cooling tower where you're evaporating water, and it's making a cold loop of water that goes through the building. And then each apartment can have its own split system, but the split is the fan coil inside the unit. And then instead of having the outdoor unit, it's connected to the water, the water that's going around the building. And there's a version, a water-cooled VRF, which is similar to this, but it's a water-cooled split system or heat pump fan coil system. There's lots of different ways of doing this, but that would be a way when you have very high rise, you just provide each unit with a tap or connection to cooling tower water, which is cooler than the outside air temperature. And so your equipment's going to operate very efficiently, right? So I would look at that water-cooled split system or water-cooled, they call it in the US, they call it the water-cooled heat pump system. But anyway, there's lots of water-cooled VRF. You can just look at that, and that would be, I think, the best for, if you have like a 40-story building, this is the way to do it. Yeah.
Right. Thank you, Peter.
A little bit more expensive, but it can be done right, very energy efficient.
Right. Next question. What is the best system for dehumidification in a warm and humid climate?
Yeah. Well, the most reliable way to provide, and I think reliability is really important, and it can be done energy efficiently. The best way to dehumidify air is you're cooling it down. And you can cool air down. When you start cooling air down, the water starts to condense out. That's why when, we have air conditioning, like if in your house you have a split system, there's water coming out there's a little tube coming out of the bottom that you need to get rid of that water. It's condensing and dehumidifying the air. So cooling air is the best way to dehumidify air. And some sort of compressor-based cooling is generally needed to provide enough cooling to cool the air so it starts to dehumidify itself. Now, there are other ways of dehumidifying air. One of them is called a desiccant system, and it's using a material that can absorb water. And so you pass air through a desiccant and it absorbs water. And this desiccant material can be painted on there's wheels that can be put in air handlers that have lots of surface area where they paint a desiccant on there, or coat a desiccant material and absorbs water. But when it gets saturated and it's full of water, it can't absorb any more water. So you have to regenerate the desiccant by heating it up. So if you have a source of heat, and a lot of the desiccant systems actually use gas or electricity to regenerate the desiccant, and then it becomes higher energy consuming than a compressor-based system if you're using gas or electricity. But there are some desiccant systems that use solar energy, solar heating, solar thermal, or waste heat from an industrial process. Often I've seen that we can now regenerate the desiccant for a low cost or low energy. And suddenly the desiccant can become very interesting. And so if you said to me, let's make the lowest energy dehumidification system, it would be some sort of desiccant connected to solar energy, but it becomes complicated and expensive. So, if you didn't have to think about cost, that desiccant would probably be the way to go. But I've looked at it multiple times on multiple designs that I've done. And every time it comes out to be more complex and more expensive. And so I've done very little of the desiccant system, but it is more energy efficient. So an efficient compressor-based system is what we go towards for providing the best dehumidification. But again, it does use energy. Yeah.
Thank you, Peter. Next question. Have you tried low energy cooling systems to achieve water temperature in radiant cooled buildings instead of refrigeration? If yes, what kind of low energy cooling system would work in a composite climate?
Yeah, so the answer to that question is yes. And what I've done in many buildings is I'll take an evaporative cooling tower using evaporative cooling, and I'll cool the water in the cooling tower, and then I can use that in radiant cooling. The beautiful thing about radiant cooling is that the temperature needed is not as cold as the temperature that we need for dehumidification or for an air-based system. So to get specific about it, we can do radiant cooling at 13 or 14 or 15 degrees C. And in many climates in India, for long periods of the year, I can make 15 degrees C water from a cooling tower. I can do that. Not at the hottest time of the year, but for much of the year. I can make 15-degree water from a cooling tower, and I can turn off the compressor. Or if I do have a compressor, it's not working as hard to take the temperature down to what is a more traditional temperature of about 8 degrees C, 7 degrees C. So that when I'm taking it down, the water down to 15, the compressor doesn't work as hard for every ton of cooling. My kilowatts per ton is better. So usually for much of the year, I can use a cooling tower only, especially in the climates, northern India and such, where they have a cold season. Then, it's very easy to use a cooling tower for a lot of the year to make the water that goes into the radiant system. But even if I were in Chennai, which doesn't really have a cold season, it's always humid, radiant system uses a 15-degree water, which is cheaper and lower energy to make the 15-degree water. So that is one of the subtle beauties of the radiant system.
Thank you, Peter. Next question. Are there any risks in using radiant cooling when it comes to the structural strength of the walls, roof, or floor in which chilled water pipes are embedded, considering the location is under seismic zone? Will it cause any maintenance issues?
Yeah, so I live in an area, San Francisco area, which is a high seismic zone. It's not a problem to put the radiant piping in the structural slab. We've done that many times in very, difficult structural systems and such. The structural engineer needs to take into account, and usually it doesn't result in extra depth, sometimes maybe a little bit. But if you tell the structural engineer, we're gonna have the plastic pipe, we usually have it, 10, 15 centimeters apart, spacing. It's really not a problem structurally. But you need to let the structural engineer know, and they need to take it into account. But I've never had a structural engineer say to me, we can't do that.
Just to add to that, the one thing probably one might need to watch out for is making sure the indoors are dry enough. We can't have in a radiant system or a building which has been cooled through a radiant system, we cannot have windows open, and you can't let the moisture in. So that if you have moisture inside, you actually have a cold slab or a panel, and then you might actually have condensation there. That's the only downside or a challenge one might have to do. So it's an operational discipline one needs to probably follow if you're looking at a radiant system.
Right. Also, we have another question following this. So one is we look at the structural aspect, and what if, the pipes in the slabs get ruptured or something? How would one, look at the maintenance on that side?
Yeah. So, in some of the emphasis buildings, there were, especially like the first one, in a big building that was 250,000 square feet, it's quite large. there were, and this is the first radiant building that this contractor had ever done. And it was the first large building in India with radiant. They had like 3 punctures of the radiant tubing where a contractor was drilling into the slab for lighting or conduit or something like that. So 3 punctures is not very many. And what you need to do is you have to chisel out the area where the leak was created and put in a new piece of pipe so it can be repaired. You know, the pipe that we're using is a plastic pipe called PEX, poly cross-linked polyethylene. It's stretchable. So if you get a crack in concrete, which you do get, there's small cracks, the PEX can stretch. So it's quite good as far as, you know, cracks and being able to accommodate that. It's not good if somebody puts a drill right into it. And then, but there is a way to repair it. It's, you know, it takes some time. It's fairly labor intensive, but it's totally doable. It's not a big deal. So.
Just to you know, just from my experience of some of the projects we worked on while I was in Infosys, you know, it's actually easier to fix them when the project is on and you've got the construction teams on site. You can identify the wet patches, you can sort of chip them around it, and you can fix them. And I think all that is done. I think what needs to be also remembered is that, you know, when you operate and maintain a building, there needs to be a certain discipline. One needs to know that there are chill water pipes in the slab, and therefore, you know, these pipes are typically about 2 inches into the slab, so you can't have a drill which is going 3 inches into it. So small, you know, operational, what should I say, a little bit of operational
Accommodation.
Yeah, accommodation. So that's something that's probably more difficult to manage because you have everyone working. You have a fit out which is done. You have an interior which is done. You don't want to have a leaky roof there. So all that is something which you do. But it's easier to fix during construction. It's more difficult when it is in operation.
Right. Thank you. Next question. What is the effect of dust on the efficiency of an HVAC system? Does dust make the design of novel HVAC solutions difficult?
Yeah, dust is an issue. And also, you know, air pollution, a lot of air pollution is actually particulates. So when you're bringing in outside air and there's dust or air pollution, it's going to load up the filter. So we need filters. If we didn't have filters, the dust and you know, particulates from air pollution would go and they would coat themselves on the coil, the cooling coil, or they would get in the ducts. They eventually get into the space, and they do really, they can get on the fan. It will have a lot of issues with HVAC equipment. It can be quite destructive, not to mention, you know, bad for human health, especially the air pollution version. So we have very good filters. They're actually very affordable. A whole array of filter options are available in India. And so you just need to pick the correct filters. And filters are rated based on what's called a MERV rating, MERV. And so generally speaking, for best indoor air quality, a MERV 13 filter is a good selection or a good choice. MERV 8 would be the minimum, at least MERV 8, preferably MERV 15. Now I'm talking about commercial buildings. In apartment buildings, there's usually not filtration. You have a little split system. If it's dusty, you close the windows, right? But in a office building where we have to bring in fresh air with the air handler, we need to filter the air. And once we do that, it's not a problem. You could be in a massive dust storm and you'd be okay inside, even when you're bringing outside air. The one thing is, when it's a big dust storm, after the dust storm, the filters will be full of dust and you'll need to change them. We have a similar situation in California, not dust, but now we have smoke from fires. And it's every year we're getting this massive quantity of smoke in the sky, even in the cities like San Francisco. And so we have to put in the filters, the MERV 13 or better filters, but we're having to change them more frequently than what we did in the past. But once you have those filters in there inside the building, it can be, you know, almost normal and no impact. So, and you know, I just to put a point on this, green buildings are better buildings. And better buildings are more healthy buildings. So we are always combining low energy systems with better filtration, better humidity control, so that the people in that building are going to have a better sense of health and well-being. And that's the beauty of more thoughtful, forward-thinking design. It's lower energy, lower carbon footprint, and better for people and safer for the people who are going to be in that building.
Right. Thank you, Peter. Next question. What should be considered important while selecting a HVAC system, the EER value or the SEER value?
Yeah, you know, the SER is, I think, slightly more, it's like an annual average. The SER is a little bit more applicable to climates where you have a big difference between summer and winter, or, you know, hot season, cool season. I personally wouldn't get too hung up on the SER. Just choose a low EER cooling system and then put it into your energy model. And the energy model will simulate the different times of year more accurately than just using the SER thing, which is sort of like a weird annual average where they say, well, winters, you know, X% of the year. It's a ARI determined metric, and the ARI, the Refrigeration Institute people, that SER is set up on climates where there's a strong winter and summer difference, like what you get in North America. So for that reason, I wouldn't really focus very much on the SER, just focus on the EER and then get it into your energy calculation or model.
Yep. Thank you, Peter. Next question. What, according to you, would be the best cooling system for a school where there are courtyards and not much of a closed environment, unlike an office?
Yeah. I mean, I think I'm not, you know, you can bring me on your team and then I'll tell you the best system, and so we can win, right? No, but, you know, I think, so I don't want to say there's one system and there's only one answer, but, you know, I love the idea of a courtyard. Lots of courtyards also have overhangs, and so you still get you can get the windows or windows that open, daylight, natural ventilation. Courtyard design is a very nice design, and it's, if you look at before air conditioning, there were lots of buildings with courtyard design. It's for a good reason. But anyway, courtyard design is about lowering the loads. And then I would so I do all that, good windows. If it's in a climate where you can open the courtyard, operable windows, things like that. Then I would have the ceiling fans would be the next, you know, layer. And then I'd see, okay, well, how much of the year do we need to supplement, and how are we going to do that? Generally speaking, when you start supplementing with a compressor-based cooling system, you want to close the windows and keep it, you know. Now, there's lots of interesting schools that have radiant cooling in them. I've seen that. But there's also lots of schools that have split system or small package unit. If you have all the right things in place before, a good building envelope, good courtyard, good, you know, good fans, the amount of cooling that you need gets less and less, and the type of cooling system is less and less important, right? So see how much of the year you're going to need a compressor-based cooling system. And if it's not very much, don't need to worry about it as much. If it's a lot of the year because your climate, then you really need to start thinking about, you know, what's the energy impact? And that's where your energy model is good. You can use an energy model to say, okay, let's do a split system, see what it comes out, and then let's do some other things. Now, if I had a school that was fairly large, remember, when we have access to water, the cooling tower based system, like a chiller connected to a cooling tower, it's so much more energy efficient. So we're doing some bigger schools, and we do have a cooling tower connected to a small chiller, and we're pumping chilled water around, and we have fan coils in the classrooms. So that would be much more efficient than split system, you know, or VRF, right? So there's no one answer. I know you wanted one answer, whoever asked that question, but But it depends on your climate and your situation and how big the school. It's like if it's just a 5-room school, that's one thing. If it's a school that's got 200 classrooms, that's a whole different thing, right? We can do the cooling tower and such with the bigger schools, yeah.
So I would say, just to add, I would say, start by asking why do you need cooling at all if you grew up without it.
Yeah.
Yeah.
That's a common thing in India. I mean,
Yeah.
no air conditioning in schools, so.
Yeah. And children generally are more resilient to higher temperatures. So, it's, as we get older, we have less tolerance. And then it's also the level of focus. Like it'd be hard to be a university researcher in a really hot part of the country and be in a room, where it's like over 30 degrees and be able to focus and get like, intensive research done. So, it also depends on the activity, whereas for children, it's no big deal, right? So, yeah.
Yep. Right. And with that, we'll take one last question for today. And that's, how efficient is it to take decisions based on simulation results?
Yeah, very good question. I like that. So simulation is a very useful tool in doing the what if question. Like, what's the right cooling? Well, I'll put these 2 different types of cooling systems into the simulation, and whichever is lower, I'll use that. So simulation is very valuable. The tricky part of simulation is that when you're inputting the information about one cooling system versus another, it's more than just saying that, it's a VRF or it's a split system or it's a, chiller. You have to input the size of the equipment, its efficiency at different loads. Ultimately, to do it right, you should put in a curve of its performance at different temperatures. And that becomes fairly tricky. And so, within the context of this project, you're not going to be able to become the world's expert on energy simulation, but you're going to want to do as good of a job as you can possibly do with a simulation. So again, there's lots of videos and tutorials online about how to do good simulation, but I wouldn't get overly obsessed with the simulation. You have a short period of time, you have to accomplish a lot. Use a simulation and make sure that you're coming out with a number that does appear to be low energy compared to what a standard design would be. And you could put the standard design in your simulation and a low energy design. You need to start seeing some reduction and significant reduction. And if that's not happening, then seek help. It would be the rapid way of getting through it. What I say to people who are practicing engineers, don't rely on the simulation alone. Our experience and measurement of buildings is the most valuable way we can design low energy buildings. Simulation is a tool, but it's not a replacement for wisdom and experience, right?
Yep. All right. Thank you so much, Peter and Samit. I think this was a very informative session today, and the Q&A was very helpful too. And I hope that our participants can make the best use of the knowledge and practices you have shared with us today. And thank you everyone for participating today. And we will see you next week at 4:30 p.m. for the webinar on cost estimation and affordability for your building.